We want to take the derivative of each of the following functions, and these are chain rule problems. So off we go. The derivative with respect to theta. Derivative of arctan of something is 1 over 1 plus that something squared times the inside derivative from the chain rule. There's not much else to do with this problem. You can write it as negative sine theta divided by 1 plus cosine squared theta if you prefer, but there's nothing else to do. Next problem, we've got a function of x to a function of x power. Anytime we have a function of x raised to a function of x power, we have to use logarithmic differentiation. So for part B, we're going to take the ln of y is equal to the ln of the tangent of x raised to the 1 over x power. We do this in order to take this power out front using the properties of logarithms. So we have the ln of the tangent of x times 1 over x, or divided by x. If you prefer the 1 over x, then you can write it as x to the negative 1 power and do the product rule. If you prefer the divided by x, then you can do the quotient rule. Most people prefer the power rule and the product rule to the quotient rule, so I will take the derivative of the right-hand side. So, derivative of the left-hand side, don't forget we have to take the derivative of the left-hand side. Derivative of the ln of y, we have to use the chain rule, so it's derivative of ln of y is 1 over y times the inside derivative, it's dy dx, equals derivative of the first times the second plus the derivative of the second, chain rule, times the first. Now, the question was find the derivative. So the derivative is dy dx. We need to solve this for dy dx by multiplying both sides by y. What was our original y? Our original y was tangent of x to the 1 over x power. So you've got tangent of x to the 1 over x times negative x to the negative 2 ln of tan x plus, and I'm just going to rewrite this with the x to the negative 1 in front of the secant squared. And that's my solution. You could write the x's with positive exponents by bringing them to the denominators. You might be able to combine some sines and cosines together on this right term here, but I'm not really interested in doing that. The question was find the derivative, and we found the derivative. The point of the question is the logarithmic differentiation, not so much trying to see if we can come up with trig identities that'll make this any nicer. So our next problem is the derivative of this ln of hyperbolic sine of t. So taking the derivative for part C, it's a pretty straightforward ln rule. Derivative of ln of stuff is 1 over stuff. The derivative of the hyperbolic sine is the hyperbolic cosine. And if you want, you can write the hyperbolic cosine divided by the hyperbolic sine to be the hyperbolic cotangent. And that's it for part C. Don't forget, the derivative of the hyperbolic cosine is the positive hyperbolic sine. That's one way that the derivative of the hyperbolic cosine differs from the trig cosine function.